Hi, my name is Abigail Hammer, and for the past year I've been studying the implementation of specifications onto a runtime verification unit. I've been working with Dr. Kristen Rosier of the Aerospace Engineering Department, PhD candidate Matthew Caldwells, and undergraduate research assistant Benjamin Hertz. So, some background. Specifications are part of a rigorous safety protocol that help define standards for an unmanned aerial vehicle or an unmanned aerial system, a UAS. Specifications help monitor the requirements of a safety critical system on board the UAS. Specifications are typically written in MLTL. MLTL is typically comprised of a finite set of atomic propositions that are connected by Boolean connectives, which are written as not, and, or, and implies, and additionally with the temporal connectives that always include time bounds, always, eventually, until, and release. Another important part of specifications is coverage. Coverage is typically a very difficult topic as we have to assess what we know that we do not know. Coverage asks the set of specifications whether or not it is completely covering all system behavior. So, for one of the specifications that we wrote RC UAS 8. It defined different rates of change for the pressure on board the UAS. The atomic conversions that we used were these two. Our pressure had to be less than our previous pressure plus our delta, and it had to be less than our previous pressure minus our delta. Our actual specification itself looked like this. It says not from globally from 0 to 3, not both of our specifications. So essentially this is saying that if our pressure changes exceeds either of these two time bounds, then our entire specification will trigger false if it happens for 3 time steps in a row and will alert the user to an error. This is very important as there are many triggers. The 3 most common ones would be rapid weather changes and rapid altitude changes, and then along with sensor failure. All 3 of these are very important for the system and can indicate severe safety hazards if this continuously registers as false. So, part of our implementation was the UTM SAT solver. The UTM SAT solver determined whether or not the specifications were entirely functional. They were, after being written in the MLTL, we ran them through a Perl script which would return if they were satisfied, unsatisfied, or unknown. This also guaranteed the model satisfied the specification. We then ran them through the realizable responsive unobtrusive unit, otherwise known as R2U2. R2U2 continuously monitors safety requirements on board the system written as specifications. It helps enable runtime verification that might interfere with critical systems whilst not interfering with the system itself, hence the unobtrusive part. R2U2 continuously outputs booleans for the specific specification for each time step, telling us if it registered as true or false for that specific time step. We ran it in simulation time implementation. This means that we did not run it directly on board the UAS. We did, however, gather our information from a real UAS test flight. As we've been working with the University of Michigan and the University of Iowa's Operational Performance Laboratory, we were attempting to see if we could run R2U2 on a Vapor 55 UAV helicopter. The Vapor 55 is owned by the University of Iowa, and they ran an actual flight test that we used. The reason why using actual flight data is important is because it can show new data that we might not have seen in a simulated flight. It helps us account for unpredictabilities. So, for part of our results, for RC UAS 8, we got this graph out of this specification. As we can see, our pressure did occasionally exceed our bounds. However, it did not do it for long enough to ever trigger our specification as false. And henceforth, we ended up with a flat line saying the entire specification was true the entire time. In order for more rigorous analysis, we injected a fault at roughly 2,000 seconds. As we can see at the end, our data continuously jumped over our bound here, which made it much more interesting for that analysis. However, this created a lot of noise at the end. It can be very difficult for the user to interpret, and so we put a secondary filter in place. So the filter would return this, and we essentially said that if our specification has returned false because it has been false for 3 time steps, but then is true, it needs to be true for an additional 3 time steps for the entire specification itself to return true. This helped filter out all that noise, and we ended up with a much more readable graph. So, after we were able to run these tests through R2U2, we are now planning for future work. We want to be able to run R2U2 on board an actual UAS system. We are still working with the University of Iowa's OPL lab to see if we can run R2U2 on board the Vapor 55 at some point in the future. We have also been working with Cyclone Rocketry, a club here at Iowa State University, to see if we can run R2U2 on board one of their rockets sometime in the future. Benjamin Hertz, one of our undergraduate research assistants, is the president of that club, and he has been working with the avionics team lead, Megan McCleary, to try to implement R2U2 on board one of their upcoming rockets. We've also been attempting to update the COTS specification laboratory, and it would help extend the coverage of the specifications that we already have and make it easier to generate new ones when we introduce new sensors. We hope at some point in the future to create a wizard for users to implement the different types of sensors they will be using on board their UAS. And the wizard will then spit out a list of different specifications that can be implemented for their UAS. This would save both a lot of time and a lot of brain power that can be used for many other things. Thank you all very much and have a wonderful evening.